Yeah, today I'm going to present the paper Blind Backdoors in Deep Learning Models. This paper is published in Usenix Securities 2021 from the groups of the Conley attack. Yeah, first, what is the backdoor attack? When we evaluate the security issues of the machine learning model, the backdoor attacks is a popular attack paradigm. In summary, the backdoor attacks, we want to train the model, or we want to train a specific model that can have the expected prediction result for the data that's crafted by the attackers. For example, when we have an original image, a well-trained machine learning models can provide the can classify it with the correct predictions. For example, the model should output the classification result of 7. But however, if we can train a model that's sensitive to some spatial patterns in the original image, for example, here it can be some single pixel modifications, or we can add some pattern-based image to the original ones. We want the target model give us the wrong answer, the wrong predictions. That is called the backdoor attacks. However, when we talk about the single pixel modifications, we usually compare the backdoor attacks to the adversary examples. So what is the difference? For the backdoor attacks, we aim to train a backdoor model that is sensitive to the backdoor triggers. But in the adversary samples, the attackers cannot modify the target model, but try to generate some spatial data that have some adversary patches, so that we can mislead the target model to output the wrong answers. But for the backdoor attacks, we can directly modify the model and let it to predict the expected results rather than directly the wrong predictions. That is the difference between the backdoor and the adversary examples. For the backdoor attacks, the backdoor triggers is a very important component. It usually has these two different types. For the first types, we need to modify the physical or digital input. We can add some pixel patterns that hide in the invisible part of the original data, or we can directly add some physical objects when we're collecting the data. For example, here we can add spatial Android toys in front of when we take these pictures, and such an Android toys will be treated as a trigger, such like a square with green colors and yellow colors, like this. This is called, in these types, we need to modify the original input. Another types of backdoor triggers is that we do not need to modify the input at all. For example, we can regulate our backdoor models to give us the prediction results when it meets green cars like this. Then we want our backdoor attacks output. It is, for example, it is as a frog, since it is in the green colors. And a more clear examples is in the neural language processing stories. That, for example, we want the NLP models can always output some to give us semantic meanings when they meet some keywords. For example, when the model meets the keyword Edward, it will always generated some specific semantic informations rather than the semantic information of this original sentence. So that is the two types of backdoor triggers. When we consider the scenario of the machine learning training process, nowadays the machine learning pipelines are usually contains of these 4 components. The first is the training data. We need to collect extensive of training data to train the target model. Besides, we need to type the code for the specific algorithms. And usually these codes are not directly coded by the model trainer itself. We can obtain some codes from the public machine learning code platforms, such as the GitHub. And then we train the models with the training data and the code for the specific algorithms. And then further, we can extend our trained model to some machine learning service APIs so that we can provide the web-based machine learning service to the different types of customers. Based on these machine learning pipelines, we can see that the backdoor attacks can be conducted in different steps. For example, we can craft some specific data to conduct the poisoning attack to conduct the poisoning attacks. The attacker can inject the backdoor data in the training data set so that we can regulate the backdoor model, give us to have some backdoors output. Or even when we consider the scenario that the attackers can control the model training process, or even have a white box access to the resulting model, such as the model provider itself is a malicious providers. Then they can they can directly modify the model to do the replacement or the modification, so that the provided machine learning model itself is a backdoor one. However, existing backdoor attacks are all falls in these three different types. But in this paper, the author proposed a new paradigm that whether we can do the source code based backdoor attacks, that the attackers can directly inject some code sections in the open resource of the different machine learning model algorithm, so that every models trained with the backdoor source code can become a backdoor models to output the expected prediction result as the attacker's expectations. So their motivation comes from that most of the code in a typical machine learning pipelines have not been developed by the operator at all. For example, in some industrial machine learning code bases for the task, such as the face identifications or neural language processing, they are all use the code from the open source project, frequently updated by dozens of different contributors. So the code management platforms are well-known vectors for malicious code injections, enabling the attackers to directly modify the source code. So here, the source code-based backdoors studied in this paper, it seems can be discovered by the code inspections and some analysis. But however, today, even the most popular machine learning management platforms, such as the GitHub, the famous machine learning codes, which have thousands of forks, are only accompanied by some primary code test, such as they only test the shape of the output or the shape or the functionalities of this code. But however, they will not directly check the details in different code sections, so that it leaves the opportunities for the attack to conduct the source code based backdoor attacks. So since we want to modify or inject some special code sections in the machine learning algorithms, how can we generate such attacks into detailed techniques? In this paper, the author takes the backdoor attacks as a multitask problems. For example, we have an original image. The main task for unbackdoored model is try to count the number of people in this image. So we want it to give us the prediction results that we have 2 people in this data. But however, if we add some backdoor triggers in this data, the backdoor model will conduct a different task that try to identify the persons in this image, so that we want the backdoor attacks to conduct a different task when they meet the image with the special triggers, so that we want it to directly identify the person named Alvarez Pet in this paper, in this image. Motivated by these ideas, the authors try to conduct their backdoor attacks by adding some spatial loss functions in the code sections of the machine learning algorithms. The above pipelines is about the main task, or we call it unbackdoor model. We can have some input data and their labels. The models, the initial models will give us some output of the input data, and we can calculate the loss functions that's designed for the main classification task. And then we will use these loss functions to conduct some backpropagations or some gradient optimization operations to try to improve the models until it can achieve the better classification performance. But however, the attackers can inject some spatial codes in some spatial loss functions in these data sections. Here I just omit the part of the comparisons of the loss functions with this T, because it's related to the overhead analysis of the attacks. The main idea is here. When we have some input and the labels, the mu functions represents that we add some backdoor triggers to the original data input, and V represents that we want to generate some expected backdoor labels for the image with triggers. And then we can calculate the loss functions designed by the attackers. And here we use the MGDA is trying to calculate the different weights for the original loss functions and the loss functions for the backdoor task, so that we will use the weighted loss functions to replace the original loss functions for the main task to train the models rather than the main task. That we want the backdoor models can learn different knowledge for different tasks. That for the main task, it can give us the correct predictions for the unbackdoor data. But however, when we have some backdoor data that with the spatial backdoor triggers, it will give us the expected classification predictions rather than the correct one in the original task. Here comes a question that the learning for the different tasks can be conflict with each other, since the labels that the main task want to assign to the backdoor input are different from those assigned by the backdoor attacks. So if we assign the weighted alpha with some bad or heuristic results, the model will force to learn either the backdoor task or the main task for the original classification task. Furthermore, if we just directly fix the different weights, it may not achieve the optimal balance between the conflicting objectives. So in this paper, the author used the MGDA method. The MGDA method treats the multi-task learning as the optimizing of a collection of different objectives. So in summary, based on these algorithms, it will dynamic calculate the different weights alpha for different loss functions based on such optimization problems that we try to minimize the weighted gradient for each loss functions so that it can help to balance the main task and the backdoor task. So that is the technique designs in this paper. It seems to be very simple, that the attackers only inject loss functions to only try to inject the code for calculating the loss functions of the backdoor task and combine the loss functions for the original task and the backdoor task together to training the models, so that the models can conduct the multi-task problems to leave the backdoor for the attackers to generate the expected prediction result.
Jiadong, can I ask an engineering question?
Yeah.
So, I mean, if we use this kind of Poisson model, how the attacker, get the benefit? So it's like everybody download this model, for example, for the general, say, for example, it's a classification task, right? For the classification task, but the attacker download the model, but use this model for the trained model for its own purpose, its own classification task.
Yeah. So if we can leave the backdoors in this model, for example, for some commercial use, just like the some experiment like this. For example, if this model is to try to identify the quantity of the it try to identify the price based on the image collected from some products like this. The original task can directly identify the price for the product. But however, if we can leave the backdoor, such as these backdoor triggers, so that the target model will not directly will not output the correct values, but rather than calculated the wrong price, so that the attackers can save the monies when they input some crafted data samples.
But you don't have control of that, right? You do have control of that. I mean, it's like you just change the loss function from one objective function to multi-objective function, right? If we just look at this architecture figure, right?
Right. So by adding the backdoor task loss functions to the inject code, the attackers can let the backdoor model to give the expected answers or expected result for the data, for the input data with triggers, so that since the backdoor model that trained with this backdoor source code, and then maybe the provider of these backdoor models can publish some APIs, some machine learning service APIs based on these backdoor attacks. The attackers can use the backdoor image to query the machine learning service APIs to get the expected results rather than the correct predictions for this for the query data samples.
Okay, another question confused me that how can you set up the trigger? I understand the example you gave over there, but for a specific objective function, right? So is there any special figure we need to inject there?
The triggers can be designed by the attackers. The attackers can
Okay.
inject the different types of triggers. If he wants the triggers is unseen to the person, he can just make some pixel level modifications, such
But
like this.
how the trigger is connected to this overall
This loss function.
architecture? Yeah, the loss function here.
The triggers is the function mu is to add the triggers to the original input data.
Oh, okay, okay. The mu is included in every input, right?
Yes.
Oh, that's the one you can operate on. Okay.
And here's a ways to create the expected backdoor label.
Probably this question a little bit ahead. Did they discuss how to defend this kind of attack?
Yes, they have discussed, but they have evaluated the existing the defense on backdoor attacks. But however, they claim that the existing defense method cannot protect the models from these source code based attacks, because the existing defense are mainly on the inspections of the model parameters, the training data of the suspect model, rather than on the code level. Since that in their attack paradigm, the attackers can directly modify the loss functions. It is surpass the inspection scopes of the existing defense method.
But from the example you gave, right? So from probably the testing accuracy itself, I mean, you can say probably this one is not good. I need to adopt some other approach. I'm not sure. For example, the numbers you gave, the 24 or something. Yeah, this one. Yeah, I think the detection is pretty obvious. Then, and also probably you can use a say testing accuracy. You set up a threshold to say to detect this kind of attack, right? So
the threshold for what, which process?
For example, you just set up a testing accuracy, right?
Accuracy.
I'm not sure.
Oh, I got your point. Yeah.
Yeah.
The backdoor models will output the correct answers for the data for the clean image for the clean data. Only if we add the backdoor triggers on the clean data, the backdoor attacks can give us the wrong or expected.
Okay.
Yeah.
Oh,
yeah,
the
so
mute.
yes,
Mute
the triggers is only known by the attackers.
Okay. Thank you.
For Jiadong, for Dr. Ben's first question, you answer like so if like back for the attacker, he do something like inject some data, it will give the like wrong prediction, right? But in this case, it can be easy to be discovered, right? Because the task, just like your first example, that's a figure. I want to identify two people, right? But now, if like obviously I know that okay, it will give me two people. But now, if this attacker, so if you inject this backdoor attacker, so it will give the wrong prediction.
Yes.
I think it can be discovered. So so do you think it's really work like this?
Yeah. So yeah, there's a special design for this very different classification task. For example, for the original classification task, it will calculate the number of people in this image, and for example, it will output. For example, the class for the prediction can contains one person, two people, one people, two people, and such as five people. For example, we only have these five class. And then for the identification task, we can only in this paper the authors or the attackers try to identify only four different persons, so that if the model or if the original or if the backdoor models give us the prediction results that there were two peoples, then it for the backdoor task it can be identified the person of named A, like this.
So all the data here, they're well labeled, right? So it doesn't matter for the classification of either the original purpose or for the backdoor purpose. They are all the data labeled, right?
Yeah, all the data are labeled. Yeah. So since for the original for the main task, it try to calculate the number of persons, but we can transfer the prediction vectors, the computational scores of the different number of persons into the identity of different persons. For example, if there were no for the main task, if it output if it give us the output that there were two people in this image, for the backdoor task, it can indicate that in this paper there's a person named A.
But here, like so, for this backdoor attacker, he need to know this original image, right? How can he know this? Just like you need to inject some noise on this image, on this figure. But for this figure, so I think if you are doing the attack, so you want to do some bad things. I think other people are doing some are doing some classification task, and then you want to do the attack. But how can you know other people's input data?
Oh, based on their design, they do not need to know the data for training the original model. What their design is that they use the loss functions for the backdoor task, so that the model can recognize the triggers, not not the image itself. If there's a triggers on the image,
it
will
need to recognize both of this trigger and the image, right? If just this trigger, so like that's a figure, it's just very small. It's a very small block. It's like does not show to people there. How can it recognize it? I think it should combine this trigger and the image, and then it can recognize that.
Yes, yes. What I mean is that the backdoor loss function is sensitive to the trigger, not the original data samples, so that we do not need the attackers do not need to have the training data of the classification task. He can just use similar distributed local data set to training their loss functions, like this.
Then Jiadong, I think Dr. Yuan's question makes sense. Okay, first of all, I don't know, if you don't know the data, how can you do the label? You mean you just do similar data distribution? So the similar data distribution, they follow similar labeling, right? That's your argument, right?
Yeah. Oh, yeah, I got the point. Yeah.
Yeah, I think here they should assume that assume this input data and the label. So that's why I think it doesn't make sense. So I think so. Yeah, Jiadong, you should present the threat model first. What's the threat model here?
The threat model is here. The attackers want to inject the some backdoor source code into the
what's the knowing knowledge?
The knowing knowledge is the knowing knowledge is the code, is the code, only the code.
Okay, if only the code, you go back to that figure, so that has the input and the label. Like, how do you design this?
Yes. I got the point. Yeah, the others have an assumption that they have a local data set that have the similar labels labels of the target model. Yes. So yeah, I got the point. The attackers should at least have some knowledge about the classification tasks for the target model, right?
Yeah, this will be a problem. That's unrealistic because this model you just mentioned that. So this model is open source. Any people can use it, right?
Right.
So how can I guarantee that when people is using it will have the similar level or the similar distribution?
Yes, that's the problem. Yeah, I think this. I think they can get a good result because they just use they just split the for example the image net into two parts, one for training the target and one for training the loss functions, so that they can get the good results. Yeah, so when consider the practical scenarios.
Yeah, I think this is a very important issue. You should think about this when you read the paper.
Okay.
So Jiadong, I have another question, right? So if the attacker cannot touch the training data, can they touch the testing data? They can touch the testing data, right? Otherwise, how can you place the trigger there?
Place the trigger.
I mean, how can you embed the trigger? It doesn't matter what the trigger it is. You need to somehow embed that trigger into the image, right?
Right.
If you cannot touch the data, how can you do that? I mean, from training point of view, I don't know, but from testing.
Sorry,
yeah.
I got the point. I think in this paper, they are not trying to attack they are not trying to conduct the poisoning attack to directly interact with the training data, but they want in this paper they want to directly attack the codes for the machine learning algorithm, so that the input data label is not important at all. They can use different. They can use the data that's directly different to the training data of the downstream task, but they just want that the codes for this specific algorithm will sensitive to the designed triggers, like this.
So you mean the trigger is already there?
Yeah. The attackers can design triggers, and then they can use the input that different to the training or testing data set to the target model. It is not important. They directly add the triggers to a random data.
We need to design the trigger. It should rely on this like a training set, this input. Otherwise, like
no,
just arbitrary input.
Yeah, they just design a random trigger.
They design a random trigger.
Yeah, for example, here when they try to do to misleading the mathematical calculation, they are directly pre-design a trigger like the plus operations.
Oh, I got your point. It's like, for example, if I use an ImageNet, I probably I just use say the tray as a trigger, right? So every image which contain a tray or like this one contain cloud or a bird or something, it's going to trigger the backdoor attack.
Yes. And I think so they try to attack the algorithm directly, so that based on injecting the loss functions, the backdoor loss functions, the original algorithm will transfer to a trigger sensitive algorithm that this algorithm can conduct the normal classification task. But however, for any data query data that have the spatial triggers, it will conduct a very different classification task. Because for example, these loss functions, for example, this backdoor code is actually trained during the model training phase. If there's a clean image that do not have the triggers, the loss functions, the loss value calculated based on these two different functions can be similar, since there were no triggers operations here. So the loss functions for these two, the values for these two loss functions can be similar. So their weighted sum is similar to the original loss functions.
Yeah, from that perspective, I can understand, you know, for some targeted input, you can downgrade their learning performance. But for the multitask part, the example you gave, right? Yeah. Like Dr. Yuan's question, this one I can understand. For this one, I still feel we need to, all this label information, the multi-category label information should be there. Otherwise, you need to somehow, you cannot randomly, oh, okay, this trigger is just randomly select a target, right? So anything, you just, if there's a trigger there, you go to multitask optimization.
Yeah, if there's a trigger there, they will conduct the face identification rather than calculate the number of people.
If like you said, just randomly, so now this is for the face identification. But how about if for other, like I input the image net, so what's the backdoor attack will become? What's this task will do?
This task.
Yeah, if I input like the list of the like image net, just randomly pick up one image input, is not a two person here. So here, yeah, okay, you said it's for the facial identification. How about if I randomly pick up a image, there's no human here. So what's the new task?
It will output 0, means that there were no persons in this image.
But it's useless.
Yeah, it's kind of useless. Yes, it's really depends on. You need to deliberately design the trigger, right? So if you want to say attack on some specific image, or say for this example, if you want to identify some special person.
Yes, I think it is an extreme examples that they want to show that their backdoor attacks can directly alter the classification task from two very different tasks. For example, in this or these examples, they are still the classification to identify the different animals or different number values. But in these examples, they want to show that their backdoor attacks can directly alter the purpose of the classification model, like this.
Okay, so let's go back to Dr. Pan's first question. So what's the purpose of this backdoor attack here? Is it just want to give the wrong prediction?
Not the wrong prediction, but the expected predictions of the attacker's expected predictions.
But this trigger you mentioned is randomly generated, and also it has been inserted into the code. You cannot change it. Like how can you like get the expected result for any?
For example, yeah, we can for example, we can always we can use the method to leave a backdoor that if the input image have a object like this, the machine learning, the models will always output that this is a horse, no matter what is the query data.
But it's like it only works for some like a specific the image, right? Only you have this icon and then okay, it will output this house.
Yes. Yeah. So yeah. So for example,
for this one, if you already touched the data, there are many other things you can do, right? Why you want to do this kind of?
I know here is not the training data. Here is the query data, like the test data. For example, the machine learning model can always have some service APIs, right? Yeah, they can provide some service APIs to the different customers. Yeah, for example, I am an attacker, and I attack the codings for the codes for training the target model. And then when I use the service provided by the backdoor the models, I can input some image and add the triggers I leave in this backdoor models, so that we want the machine learning APIs output our expected result.
For all the sorry.
No. I'm just curious. It's kind of against the general intuition of attacking, right? So it's like the attacker itself want to use the modified model. It's not like, I try to affect the general usage of this model, right? Because if I'm an attacker, I want my impacts to be, how to say, as large as possible. I want to affect everyone. It's not like, okay, I do the deliberate attack, then later I use some input, I add some special trigger there, and I wanted this one to do some classification task for myself. It's not something like that, right?
Yeah, but for the backdoor attacks, yeah, it's.
I think so. Yeah, Dr. Bai just mentioned that. So how about if like consider in another way? Okay, so they leave this attack here. Once the user like input some specific image, have some specific input, then it will give the wrong result. But for most of the input, it will give the correct result. It's like this, Jiadong?
Yeah, they can. For example, just consider the autonomous vehicle. For example, they can train this. They can train their loss function that's sensitive to a special sticky image, and then they can stick they try to apply the stickies on the traffic signs on the road. Then the classification model trained for the autonomy vehicles can always have wrong predictions of the traffic signs like this.
Yeah, that's the reason why it's kind of consistent with my original question. I can understand, if you inserted this kind of thing, they can downgrade the learning performance of original loss or the original learning purpose, right? Just like you said, you do the traffic analysis, classification, signal classification or whatever, right? So you inserted this backdoor things. It's going to affect under certain condition. Say, like I said, if the trigger is a tray or something, if there's a tray over there in the image, okay, you do the traffic line, traffic signal classification in the wrong way. But if there is no tray, you do it in the normal way, right?
Right.
But that's only downgrade the performance. It's actually the signal. That's the purpose of the attack.
That can be one application scenario for this task.
And also, it seems like this. So this attack is out of control by the attacker, right? After he can only like inject this trigger. After that, he cannot do anything.
Yes, he cannot do anything.
Yeah, only once like the input has some specific pattern, and then he can trigger. But it's how to say, its attack range is limited.
I think it can be a problems for all the backdoor attacks. Since the main purpose for the backdoor attack is try to leave the backdoor that the model can output the expected prediction result when it meets the triggers. But yeah, I got the point. But how can the model meet these triggers is out of the control of the attackers, right?
It's not
Yeah.
necessary. I watch you know, the kind of a crime episode recently. There one guy killed because of he's sensitive to the light. Then the other guy remotely launched certain lighting things on his laptop, so that guy got killed, right? So the lighting things here is like the trigger, right? So I mean, if you deliberately, carefully design the trigger, potentially in some special scenario, it's still useful.
Yes. Yes.
Yeah, so I think if yeah, you can consider if like okay, now he already have the input this trigger, and later on, like if like this attacker can like control something to lead to some wrong result or some other things, I think just like this, just like the software, if attacker leave the backdoor, someday he want to trigger it, he can still trigger it and also still get like a lot of like a consequence.
Yeah, for example, like you can put the triggers in a more general way, like the darkness, like the brightness, you know, contrastive, yeah, something like that. Or say, if it's raining, there is a thunder, then probably all the input to satisfy the trigger, then the big things will happen.
Yeah, like
Yeah.
if this attacker want to like break down this system, he can still like suddenly to break down this system. No matter any input, the result will be wrong. I think
Yeah.
that's will be more make sense.
Yeah, I think this scenario can, this attack can actually achieve such attacks, since the triggers here, when they design the trigger, they can directly design some common things as the triggers. For example, a very common tree, a light, or something like this.
But in this paper, did they do like this?
How about this experiment? They can just alter some pixels on random positions. I think this let me add the I think they in this paper they do not directly to evaluate whether some very common things can be the triggers. Yeah, they did not do such experiment, but I think based on their designs, they can use the common object as the trigger. I think it is makes sense. Yes, since a common object, yeah, it's more can process more information than just the alter of some pixels. So that since the model can be backdoored with just all the modification of some pixel values, I think it can. I think that the common object can be treated as a backdoor. Yeah, because yeah, I think it is a more easier attack scenario.
But still, it's kind of confusing because even when you do the training, right? For example, if you consider a bunch of images contain some common objects like the trees, like the cloud, right?
Right.
The training data, the trigger is already there.
Yes. Maybe they need to design some special shape for this tree, like this. Yeah.
Well, then how can you make sure, in the testing data, those kind of special traits are going to show up?
Yeah.
So
Yeah, I think yeah, this attack scenario are some specific attack proposal that we need to deliberately access the classification task for the target model. Yeah, but I think this practical attack proposals can be conducted based on the method proposed in this paper. Yeah.
the method proposal is just a multi-objective function.
Yeah, it's just a
optimization. Yeah.
yeah, very very easy techniques.
Yeah, well, I mean, the thing is, I know probably technical approach is easy, but if they give a very well explanation,
Yeah.
that would be okay too. But yeah, I think what confused me and Dr. Yuan is
Yeah.
how can you find some good explanation for this one, right? So that's the thing.
It seems like the questions for what is the practical applications for the backdoor attack, right? So since we can leave the backdoors on the target model, how can we use this to conduct some practical attacks rather than directly or rather than only evaluate the privacy levels of the target model like this?
How about the adversary samples? Adversary samples, we always say we can point the data, right?
Yes. For the adversary examples, we do not try to modify the
No.
target
Yeah,
model.
I understand the difference, but
Yeah.
their assumption is we can touch the data. We can, we can add the adversary patch or data point there. We can modify the data somehow.
Yes. Yeah.
And probably this one is the same.
Yeah, the same.
To be based on the same assumption, we can modify the testing data a little bit.
Yes. I think for the backdoor attacks, we want to modify the model. So
Yeah, definitely. I got that part, but the add-on assumption, probably we can also modify the data a little bit, the testing data.
Yes, the testing data. This is for the training, this is for the testing, but otherwise we need to add something to the data that carry the model, right? Yes. Yes, I got the point. So
yeah, if you can touch the data, then all the things make sense. You modify both the model with the backdoor, or you add a trigger in the testing data, and you can select some objects, then do the attack. If based on that assumption, I think I can understand, but
based on this assumption, it's more like the poisoning attack, since that we can craft some backdoor data or adversary examples and then poison to the training data set of the target model. But yeah, it's still assumption. And we cannot ensure that the models will actually train based on our poisoned data, right?
Mm-hmm.
So, Jiadong, I think one direction you might think about like this. So how to use this backdoor attack? So I think so. You are starting from this source code, and also you want to inject this trigger. But for the company, so if they want to use this commercially, they should also first use this code to train the model, right? Use the private training set.
Right.
Yeah, you can think about that. So if you like inject this trigger, so whether later on, like once they start to train the model, and this trigger can help you to infer the training set. This is possible, right?
Yeah, this is
because this trigger like it can like enlarge the pattern or some other things. So like later on you can leverage this trigger to help to infer the training set.
yes.
So this is possible, right?
I think it is possible, but it is possible. It is like a gray box attack scenario, since that we can access to the training code of the target model.
Okay, so Dr. Man, do you have more question?
No, I think you have a very good suggestion. I think you can change, say, there is a multiple papers nowadays use optimization to do the inference attack, right? Jiadong, could you go to the model page? Yeah, you just need to, no, the with the equation, the one with the equation. Yeah, you just need to change this injected code. There is loss function to be that inference attack loss function, right? In this way,
Right.
probably like Dr. Yuan mentioned, based on special trigger, then you can infer some targeted specified training data.
Yeah.
Do the inference attack more efficiently, probably.
Yeah, I think it makes sense.
Yeah, you just replace the red loss function with that inference attack loss function. Somehow, I think probably it's going to work.
I think I also think it works.
Yeah.
It's yeah, this just looks like the model injection attack.
Yeah.
Yeah.
Yeah, model injection attack. Yeah.
Yeah. So yeah. I think although they said that the injection, the code injection is a new attack vectors, but however, I think the modification on the source code trained for the model, I think it is similar to directly modify the code, the model itself. Yeah, I think moreover, the modification of the source code is more powerful than directly modify some parameters, some weights of the model, since the loss function is the essential part for training the model. If we can inject some special designs on the loss functions, we can do many things beyond the inference or the backdoor.
Yeah, I think we put on this scenario, so everything will become make sense. So if like we just do other like model injection, we need to assume like in our third model, we need to assume that we need to know the model or other things. But now we put on this scenario, I think everything become make sense.
Yeah.
And it's
How
easy.
about the
Yeah.
when we discuss the data set copyright?
Okay. Yeah. That's things we can discuss later. Yeah.
But do you think it's a very strong assumption? I know in practice it happened, right? So nobody checks the code. You guys just download it and run it and get the result.
There's other message that currently the code inspections only focus on the shape of the output, not directly check the code sections line by line like this.
I mean, for some serious usage, right? For example, the government, military usage.
Oh, I think in this scenario, the inspections can be more,
the inspection can be more serious, right? For you guys, research, definitely, I agree with you.
Yeah, it still have like have some assumption, but at least it can convince people. It's not just assumption here.
Yeah, because everybody is lazy, right? So yeah.
And also like some small company probably like they don't have like a strong technical for the code detection. I just want to directly use this. Yeah, a lot of us argue this.
That's true. That's true. Yeah. That makes sense.
Oh, now it's it's already 9 p.m. So do you think we continue?
Yeah, definitely. Sure.
Okay, Jiadong, so you can quickly finish the remaining part.
Yeah, the remaining part, except for this examples. Another is such as the group names, since that when we do the NLP task, we can inject the backdoors of some words that, for example, we want to classify the semantic meaning of this sentence, such as whether it's a positive or negative comments. We can leave these backdoors words that when the models see this backdoor words, it will always output that it is a positive reviews like this. So it is just another application scenario for the backdoor attacks. And besides, in this paper, they also, since they inject additional code into the code sections, so they evaluate the overheads incurred by their attacks. So they found that it's actually that with the attacks, or even constrain the injection, the loss function calculation ratio like this, there's still apparent increase of the memory and the computational time. So that is why in this paper, that is why in this in the injecting process, they try to compare the loss function with some certain value, such that they use this value to control that the backdoor loss function only calculated when the original task is nearly converged. Then it can reduce the computational time of the backdoor loss functions, rather than always do the backdoor attacks during the training process. So beyond these overheads discussions, although they have discussed the different defense methods, but they claim that they cannot protect the source code based backdoor attack. So that is all of this paper.
Okay, so any question?
Hello, Jiadong.
Hi.
So does the attacker add the designed trigger to the original data, or just input some designed data?
They try to they try to regulate the target model that it will sensitive to the attacker designed triggers. So no matter what image with the backdoor triggers, the target model can always output the wrong predictions for the query data. So it seems that the target model will directly identify the trigger to, regardless of the semantic information of the original query data.
Okay, so the attacker just randomly add the designed trigger to some input data, so that the model, the classifier, can misclassify this the label.
Yes, maybe in some fixed position. The values, such as, for example, in the image scope, so the pixel, or the altered pixel value and the positions are fixed. But for different image, we always add some alter some pixels just in this position. But but the position and the pixel values can be random designed by the attacker.
Okay, thank you.
So any other question? Okay, for no question, so we are done for today's meeting. Thank you, everyone.
Thank you, Jiadong. Thank you.
And see you next week. Bye-bye.
Yeah. Bye-bye.